Hi everyone, my name is Igor Kolak and I will present the paper that four of us participated in. The topic of the paper is Realization of Automotive Video Data Acquisition System for Usage in Evolution of Autonomous Vehicle. I hope that you will find it interesting as it represents cutting-edge platform not just for acquisition of camera streams but as well as the platform for development of advanced driver assistance systems, so-called ADAS algorithms. First, I will explain motivation for creating this video data acquisition system. As you already know, automotive industry players are competing with each other in order to reach level 4 and level 5 of autonomous driving. They are investing a huge amount of money in order to develop machine and deep learning algorithms that will be used to predict vehicles' next move. But before they could start mass production, all these vision-based systems must be properly tested, which means a lot of tests with real-life scenarios must be conducted. Basically, autonomous vehicles would have to be driven hundreds of millions of miles and under some scenarios hundreds of billions of miles to create enough data that clearly demonstrates their safety. They would have to scope different driving scenarios with different conditions, all kinds of roads, etc. It's not an option to put that vehicle on the road and let it be verified in the real world, as human life is most valuable thing. That being said, algorithms must be verified with real world data but in the safe and controllable environment. In order to do that, we must create a specific platform, so-called frame grabber, that will collect the data from cameras and store it for offline usage. In order to be competitive with others, the platform has to solve several things. So, the first challenge that needs to be solved for an automotive video grabber is to gather the data with cameras that will be used in the car itself. Why is that important? Well, because the ADAS algorithms that are being developed will eventually end up in the car, so they need to be fed with the frames from the exact same cameras that are mounted and used in the car. The second one is that the saved video must not be degraded, meaning it must not lose any information when stored on the disk. That means it must be stored uncompressed, or it can be compressed using lossless compression in order to stay valid for training and verification of the algorithms. There are some already available video grabbers on the market. Some of them support all kinds of interfaces and can store all kinds of signals, but at the end, most of them don't support automotive cameras grabbing. Some of them are really good and have an interfaces to the cameras and ability to grab camera streams, but they lack some other features like image signal processor, or they can be used as a development platform as well. Here we are presenting mini video logger device. Central unit for acquiring and processing streams from cameras is Texas Instruments TJ2PX SoC. It's surrounded with 4 GB of RAM with additional 1 GB for error correction code memory. Firmware can be stored on either 32 MB QSPI flash chip or SD card. Using CSI2 camera serial interface ports, the SoC interfaces 2 Texas Instruments deserializers hubs, each containing 4 camera connectors. Basically, one would be able to connect up to 8 cameras to the system. The cameras are powered from the board itself using power over coax, so no additional power supply is needed. Using 4 lanes PCI Express connector, it can fit in regular PC and act as an endpoint device, or it can, for example, interface NVMe disk and act as a root complex device. It also has SATA port, so the disk can be also attached there. With 2 gigabit Ethernet ports, it can interface PC for either control of the system or to send the data to the PC. Additionally, it has USB 3.0 port, RS-232 planned for GPS, CAN and CAN-FD for attaching to the CAN bus, and HDMI port, so the picture from the cameras can be directly displayed on the monitor. The good thing is that the TDA2P SoC is already used inside the cars for processing ADAS algorithms, so the mini video logger can be used as a development platform as well. That being said, it could minimize the time needed for porting of the algorithms, as the exact same SoC can be found in the car already. Once finished with the data acquisition, one could use benefits of supporting software development kit that comes with the board to minimize time to develop ADAS algorithms. The use case is represented as a graph connecting processing blocks and thus forming a processing chain. Each block in the chain encapsulates separate function. After the algorithm is made, the board can easily fit into regular PC via PCI Express connector and act as endpoint device. So one could feed the developed algorithm with the acquired data and benchmark it easily. Or one could use the board as a standalone device and feed the algorithm with the data stored on any kind of disks. For example, NVMe disk interfaced via PCI Express, SSD disk interfaced via SATA connector, USB memory stick, or transferred the files directly via Ethernet connectivity from the PC. A bunch of building blocks is already available from the SDK itself, so developer can focus on its algorithm block only. As you can see, one frame of 2 megapixel camera in YUV422 format takes about 4 megabytes. As we have 60 frames per second, that sums up to 237 megabytes per second. The used Intel Optane 900p disk has about 280 megabytes per second write speed, so the calculated 237 megabytes per second fits there. For the evaluation of the board, the use case for benchmark and evaluation is created using provided SDK. It takes one camera stream and writes it to the disk. The ARM Cortex A15 CPU load goes between 47 and 51%. So this shows that platform is able to provide sufficient bandwidth for 2 megapixel 60 frames per second, so one could use it, for example, to store 2 cameras of 2 megapixels at 30 frames per second, or any other combination of resolution and frequency to utilize up to 8 cameras. Potential future work is to play with the optimization, such as benchmark different disks or try to use disk controllers, etc. That way one could speed up the read and write performances and provide more bandwidth. The question that has arisen is what makes the platform unique. I would like to emphasize that other solutions are using specifically designed FPGA hardware, while our platform uses automotive designed SoC, meaning one can easily utilize some of the processing power for real-time manipulation of the camera image, so no additional read it offline processing is needed. Another originality is that while it can act as a grabber device, it can also be used as a real development platform for the exact same SoC that can be found in the car already. The platform is designed so it exposes numerous of interfaces, so the end use case of the platform is not limited by those. Thanks for watching.